Hey y'all, are you liking the conference so far? Yeah. Cool. All right, my name is Mateus Guimaraes. That's very hard to pronounce, so Mateus is fine. I've come all the way from Brazil mentioned. So I don't know, give me a Brazil. Okay, cool. And I want to thank the conference, the speakers, the staff, everyone, and especially my wife who's in the audience and has always been very supportive of me. And yeah, let's get this started. So, a little bit about myself. As I said, my name is Mateus Guimaraes. I currently work at a company called GiveButter with some very smart folks, much smarter than me. I'm also a content creator, mediocre guitar player, and you can find me on Twitter, you can find me on YouTube. Those are the places I'm usually hanging at. I have a YouTube channel where I talk about architecture, software design, PHP internals, Laravel internals, all of this stuff. So if you're interested, do check that out. I also have a Laracon course on modularization called Modular Laravel. If you're interested in that, also check that out. Today we're going to talk a little bit about Laravel Octane. Who here is familiar with Octane? Raise your hands. Who here has used Octane in the past? Okay, cool. So, this is straight from the docs. Octane boots your application once, keeps it in memory, and then feeds it requests at supersonic speeds. Now, this could be my talk. Everything you need to know about Octane is in the documentation. So instead of talking about what Octane does and how to use it, which is very thoroughly described in the documentation, we're going to talk about which problems is Octane solving exactly, why doesn't PHP do what Octane does by default, what is it abstracting, what are the lower level libraries that Octane is using to make that possible, and what else can you explore besides Octane? And to do that, we need to understand how a typical PHP application works. Who here knows how PHP-FPM works? Raise your hand. Okay, cool. So the way that PHP-FPM works is you get a request from a user that goes to Nginx or Apache, working as a reverse proxy, and then that goes to PHP-FPM. PHP-FPM will do one thing. It will boot your application from scratch, serve the request, destroy the application, clean the memory space, and then send the response back to the user. So essentially, with PHP-FPM, you always have code stars. A lot of the code is cached by OP-cache if you're running OP-cache, but you still have to execute the application from scratch. What Octane does, essentially, is to add an adapter in between your Laravel application and your web server that is going to keep that application long-lived. And it uses a few different runtimes to do that. You have Swole, you have OpenSwole, which is a fork of Swole, you have FrankenPHP, and you have Roadrunner. And Octane acts as a base abstraction that allows you to communicate with all of those without having to worry about them. And the way that those work is you have a user. Before a request comes through, the application is already booted in memory. And when the request hits Octane, hits Laravel, the application is already warm. So you don't have to boot any of the providers. You can just serve the request. And that's one of the reasons why it's so much faster. So you basically eliminate an entire step. A good example of something that also only boots once are queue workers. Who here has had memory problems with queue workers? Raise your hands. Okay, a lot of people. And that's because queue workers only boot once. If you look at the code, you have a bunch of things, but you have a while true loop. So that loop only ends if the worker crashes or if you manually end it. That's a good example of something that only boots once, that has the application warm, but that's outside of a request context. For us to talk about how these things work, we need to refresh our minds a little bit, go back a few steps. One question. How many things can a CPU core do at any given time? I know that you guys watch Prime, so you know the answer. Does anyone know the answer? One thing. A CPU core can only process one instruction at any given time. And there are a few ways that you can process tasks. You have synchronous and sequential execution, where you have a CPU core, you have a task, it does a task completes it, and then moves to a different task. You also have parallel execution, where you have multiple CPU cores, and each one is doing one thing. And to better utilize our computers, we have concurrency, in which you have a single core just jump like crazy between tasks. So if you're waiting for something, if you're waiting for an operation, the kernel's not going to wait for that. It's going to do something else and come back to it. That's why even when we had single-core computers, you could do more than one thing. We have a few building blocks when it comes to program execution. You have your operating system, you have processes. Within processes, you have threads. Within threads, you have ring threads, which are user space threads. We're going to talk about them briefly later. Think coroutines, go routines, that sort of thing. You have the kernel managing all of this, at least the processes. So essentially what the kernel is doing is you have a bunch of processes, and it is allocating CPU time for each one of them. And as soon as you get a blocking operation, it goes, OK, I'm not going to wait for this. I'm going to do something else and come back to this. The reason I'm talking about this is because we need to understand how PHP-FPM works. The way that FPM works is requests are processed sequentially. So that first example, you have PHP-FPM managing those workers, and you have a pool of workers that you start with. This is all configurable. So let's say that you start with 2 workers. You get a request. PHP-FPM goes, OK, I have a worker available. I'm going to assign this to this request. You get a second request. OK, I still have a process available. Let me assign that to that request. Now, if you get a request and you don't have a process available, PHP-FPM is going to go, OK, can we spawn more processes? Do we have any spare? If the answer is yes, it is going to fork new processes, which is a relatively expensive operation. If you get a new request and you don't have processes in the pool, you cannot spawn any new processes. FPM is going to move that into a request queue. And essentially, that request is going to hang until a new process becomes available. Who has dealt with that in the past? Having requests hang? OK, plenty of people. So essentially, with FPM, the number of concurrent requests you can serve at any given time is the number of processes you have. So you only handle one single request at any given time per process. It's always booting the application. If you have blocking I/O operations, the request is going to hang. And if the processes are busy, they're going to go into a request queue. We call this a shared nothing architecture. Each request is handled by process. They're all individual. You do not share any memory space between requests, which has some benefits. It's relatively easy to scale. You can just add more processes, and it is going to work. You have some level of fault tolerance because the requests are isolated. If something crashes request A, that doesn't affect request B, C, D, or E. And you don't have shared state, which makes debugging much easier because you can always expect a request to come with a clean state. It also has some downsides. Sure. You have the increased overhead because you're always starting your application from scratch. Processes, from a task management perspective, are expensive. And you have some limitations when it comes to persistent connections, for example, WebSockets and connection pooling. You also have long-running architectures. And this is just a generic term to describe everything else. And generally, you have a single process or a single process with threads handle one or many requests. You have applications running as long-running processes like queues, so we are all familiar with those. And in some situations, you can have a single worker handle multiple requests concurrently. Some examples, Rails with Puma. Node.js is a single-threaded process that uses an event loop. .NET. Most languages follow this architecture. Benefits, you don't have to boot your application all the time. You have connections to your databases, to your cache, whatever you're connecting to. They can be persistent because you have a long-running process, and sometimes you can do things concurrently. Some downsides. The downsides are pretty much all of the upsides of a shared nothing architecture. Now you have shared state. You can affect other requests. You always had memory leaks, but if you have a long-running process, just like a queue, it could crash the process. And it is less predictable because you cannot expect our requests to always come with a clean state. So something you're always going to see being mentioned when someone's talking about requests and server and all of that is non-blocking I/O. What does it mean? I/O operations such reading from a database, reading from a file, reading a cache, making an HTTP request, in PHP are by default blocking. they block the process. The process cannot do anything else while it's waiting for a database call or for an HTTP call. We call this blocking I/O. There are some solutions to do non-blocking I/O, and you're going to see that mentioned very often with Node. Node is an example of an event loop. That's a way to deal with this. You also have ring threads. If you use Go, you have, for example, Go routines, which are not exactly coroutines. They're managed by the Go runtime. You have multi-threading. And then in the bottom, I left some keywords. If you want to go a little bit further in this, a little bit deeper, you can look into file descriptors to understand how servers work. You can look into some system calls to understand how, for example, some event loops work, and some low-level libraries that are used by many projects, including some that we're going to talk today. So here's an example of some JavaScript code. I imagine everyone here is familiar with JavaScript. And something that you can notice in JavaScript is it relies a lot on events. Here you have an event listener, so you are storing a callback to a given event, and you're saying that whenever a click happens, you want to console log something. Now, that code, it is being executed synchronously. The callback registration is being executed synchronously, top to bottom. The callback itself is not going to execute until an event happens. The way that Node does this is through what we call an event loop. And you can think of an event loop as just a loop that never ends. And you have two important things. You have the event queue, and you have operations. Operations are tasks. It could be reading from a database, reading from a cache, reading from a file. And what this event loop is going to do is it is going to receive registrations. I want to register this handler to this event. And whenever an event is emitted, it is going to pass that to the operation you want to do. It's going to execute that callback. While that callback is being executed, the event loop is going to do something else. It's not going to wait for it. So that's how Node works, for example. If you're reading from a database, okay, I'm waiting for Luke to give me an answer. I'm going to do something else. I'm going to talk to other people. When he's ready, I'm going to come back. If you're a party host and you're dealing with many hosts and someone asks you for a cup of coffee, you're going to go to the staff and say, hey, I need a cup of coffee, and you're going to go do something else. When the cup of coffee is ready, you're going to pick that up and deliver that to the person who asked it for it. So that's more or less how an event loop works. And we're going to use an event loop as an example because Swole, one of the most popular ways to run Octane, uses event loops and coroutines. But essentially, whenever you have non-blocking I/O, it's something similar to this. If you're using the Go runtime to handle this, it is abstracted for you, but it's doing something similar. So this sounds very complicated. I'm not sure where this is going. Where's this used? Who here has worked with Node.js, with Express? A bunch of folks. Express, as you can see, also uses this. You have an event, which is a request coming through, and you have a handler, which is a callback. You can see that callback's not actually returning anything. It's calling a method within the response object, but it doesn't return anything because it's handled asynchronously. At some point, we don't know when the operation is ready. It could be 10 seconds, it could be 15 seconds, it could be 100 nanoseconds. The web is essentially I/O. Most of us are not doing CPU-bound tasks. We're talking to databases, we're talking to caches, we're talking to other APIs, we're talking over the network. So a lot of what we're doing is I/O. And a lot of what our applications are doing is waiting for I/O, which is just wasting CPU cycles. So what if, just what if, we could run non-blocking, long-running PHP programs like these other languages do? And although PHP-FPM doesn't do that by default, we have other runtimes that allows us to do so. We have Swole, we have OpenSwole, which is a fork of Swole. We have Roadrunner, we have React PHP, and we have Franken PHP. You have plenty of options to pick from. There are some differences between them. Swole is written as a C extension, also uses C++. It uses event loops and coroutines. Franken PHP is written as a Go extension, and Franken also comes as a SCADI extension, which means you can replace Nginx with it as well. React PHP is a low-level PHP library, and Roadrunner is also written in Go. So they do things a little bit differently, but they all try to achieve more or less the same goal. The problem is that PHP was not intended to run like this. This is not to say this was a mistake. This was a choice, a design choice. You have benefits with shared nothing architectures. And PHP is very fast. So in most cases, having that boot overhead is not a big problem. So given that PHP wasn't intended to run like this, neither was Laravel, which means that you can just pick your Laravel application, throw swol on it, and say, OK, I'm good. You're going to have problems. Let's look at how a Laravel request is handled. This is from Laravel 11, so it's recently become a little bit more abstracted, but it's just top to bottom. You have a request coming through, you have your super globals, you know what to expect. You call the handle request method from Laravel, and you know that afterwards, their request is going to get destroyed, that application is going to get destroyed, the memory space is going to be cleaned. You don't have to worry about it. Now, pretty much you get a request, you boot the application, you destroy the application, the request is sent back to Nginx. This is how swol handles a request. So you can see that it is pretty similar to Node. You have an event, which is a request, and you pass a handler to that event. You say, OK, whenever we get a request, I want to attach a header to the response, and then I want to end the response, which means to send this. And then you have this little guy right here. And what is this little guy doing? Does anyone have a guess? This is a loop. This little guy means that this code is never going to stop running. So whenever you run swol, you have a long-running process. That guy makes sure it is going to keep running. And then as requests come through, swol is going to execute the callback you registered. Pretty different way to handle things from PHP-FPM, right? Don't you agree? No? OK, we agree. So writing this sort of code is a very different paradigm as compared to writing PHP-FPM code. Regular, synchronous, you know what to expect code. And that's where Octane does the magic. What Octane does is it allows you to run your regular Laravel applications, your regular synchronous Laravel applications, as you have always written them within this context. So, OK, this talk is about Octane internals. If I were to talk how to use Octane, you can check the docs. What I'm really interested in is how does it work? What is it leveraging? How does it work? Octane does a lot of things. First of all, it boots the workers. All of those runtimes use the concept of workers, which is a process, exactly like a queue worker. It's a long-running process that's going to receive requests. So Octane does the job of booting those workers. Here's an example of how Octane boots a swol worker. Notice that you have the same pattern. You have an event, which is worker start, and you have a handler. Now, there's a lot of code here, but I want you to pay attention to two things. Have a onWorkerStart object being called, and you have a worker state variable also being passed. The reason Octane does this is because it is going to store the worker on that worker state variable. Remember, this process is never ending. The code doesn't stop executing. So this is going to get stored in memory. If we look at the onWorkerStart code, you're going to see that we are booting a worker. We have this boot worker method. It does a bunch of things. But one of the important things it does is it boots the application. So by the time the worker starts, it already boots the application. It saves that application on that worker state variable. And now you can use that warm application to serve all of your requests. You don't have to boot it once again. It also forwards those requests in a long-running environment. Like we've said, this is a very different way to run Laravel applications. So what Octane does is it will convert those requests into something that Laravel understands. If we look at the swol example, you also have a lot of code here, but you have an event, which is a request. What we talked previously was worker start. This is request, which means your application is actually receiving a new request. It does a bunch of things, but look at this block of code. Remember the worker state variable we talked about? It is being used now. And we're passing a request to our worker. And what Octane is doing is it is converting a swol request into an Illuminate request, like this. So for the swol client, it is going to convert that into something that Laravel understands. For the front-end PHP client, it is also going to convert that into something that Laravel understands, and the same goes for Roadrunner. So Octane provides a unified API that works with all of these drivers, or rather, that converts what those drivers give you, those runtimes give you, into something that Laravel understands. And you don't have to worry about that. This is the library's code. You're not touching this. You don't even know it exists in most cases. If you have a warm application instance, it means that you have to handle requests in a different way. The regular Laravel kernel is not going to work in this situation. You don't have access to super globals. So for one, that wouldn't work. The system code, there's a lot going on here, but I want you to pay attention to two things. You notice that Octane is cloning an application instance. The reason it does this is you have a warm application instance that just booted. It hasn't been mutated yet. You're going to serve a request with that. If you serve a request with that instance, it's going to get mutated. And then when the second request comes through, it has mutated state. It's been violated of sorts. So what Octane does is, first, it turns that into a sandbox instance. It clones that so you can use, and you still have that fresh, warm instance the way it was initiated without having been mutated by your application. And then it passes that into your application. So it essentially handles the request. After it handles the request, it spits out again a slow response, because remember, we are in a driver context. So, I'm sorry, not a slow response, an Octane response. So it's converting that into something that Octane understands, so that therefore Laravel will understand. And then it terminates the application. Again, this is something you don't have to worry about because Octane handles it for you. This is how the Franken driver handles it. It looks a little bit more like common PHP-FPM code, but you still have that within a closure. All of them are going to use closures because you don't want this code to be executed at the start of the script. You want that code to be executed when a request is handled. And that's going to happen several times within a single process execution. So same thing. You're putting a worker, you're assigning that to a variable. That's a long-lived variable. And you're passing a request. And then in this block of code, you're actually passing that to FrankenPHP. So you have FrankenPHP handle request, which is a function that the FrankenPHP C extension will provide for you. Flushing framework state between requests automatically. Remember that I mentioned that with long-running processes, you have problems with global state? PHP typically uses a lot of global state, precisely because we can assume that a request is always going to come up clean. We don't have to worry about it being mutated by other requests or other workers. This doesn't work in a long-lived environment. So what Octane does is Octane itself emits several events during the request lifecycle. When a worker has started, when a worker has finished, when a request was started, all of those are available to you to use in your application as well. But Octane also uses that to do a bunch of things you would have to do manually in your application. And you look at this and think, okay, there's not a lot of listeners here. Until you look at the methods, and you have this. So we're not really interested into what each one of those are doing. It's just to show that there's a lot going on just to flush the framework state and the first-party packages straight. And if you were to run it yourself, you would have to do this. And I can bet that you would forget about one of these. I would. This is the other method, which also flushes a bunch of state. So it does many other things, like gracefully restarting workers. With Throw, we have a high-performance cache that you can use. You have to run the garbage collector every once in a while. Octane also does that for you. You have some conveniences like watching for file changes, things that you would have to do manually. So essentially, there's a lot going on that Octane is abstracting for you that you could do yourself, but I don't think it would be pretty. Okay, so we talked about lots of things. What about that non-blocking I/O thing you mentioned earlier? You haven't come back to that. So non-blocking I/O is a little bit trickier. Let's look at some code. We have a very simple route. We have a slip function. I use the slip precisely because it's simple. What happens when you slip for 5 seconds and you make a request to route? The process hangs. The process doesn't do anything for 5 seconds, and then it sends a response back. This is a blocking I/O call. Most PHP functions are blocking by default. The ones that are I/O operations, like sleep, reading from a file, talking to a base, they're blocking. So if I run a benchmark on this, it's pretty horrible. I'm doing like 0.2 requests a second. That's awful. So what can we do to handle this? Well, SWO specifically provides a go function, which essentially means execute this within a coroutine. And a coroutine, as we mentioned, is a user space way to handle concurrency. We're not going to go deep into what a coroutine is and how it works, but SWO provides it for you. So you think, okay, what if I add this go function and pass a closure and call sleep? Will that work? What people usually think is yes, because you're executing that within a coroutine. But you're still executing a blocking call. So that will not work. For SWO specifically, SWO provides replacements for most of the native PHP functions. So this guy right there is a blocking IO call. This guy right here is not. So SWO allows you to either call them explicitly by using the SWO replacements of those IO calls, or you can also configure SWO to replace them automatically for you, and you can still use your native function. So if I run this instead, the SWO version inside a coroutine, then I get much better results. The same non-blocking call, things are better. Your application is more performant. So when people see Octane and they see SWO and they see FranklinPHP, they think, okay, now I can have a single worker serve 10,000 requests concurrently. And sadly, that's not always true. If I look at another example code, what this is doing is it's a select call, it's actually hitting the database and it's telling either by SQL or Postgres to say, hey, sleep for 1 second before giving me a result. If I were to execute this, even with Octane, it would still be blocking. And maybe that's not intuitive because you think that with those runtimes, you're getting non-blocking IO for free. That's not always true. So if you execute this, it is still going to be blocking, even if it's inside a coroutine, because the underlying function call is blocking. However, there's something that you can do with Octane and with SWO specifically, that is to run things concurrently. So we can call the concurrently method. You can pass a series of callbacks. You can also return those values so you can grab them back. And you can pass a list of operations you want to be executed concurrently. What Octane is going to do behind the scenes is it is going to forward those operations to what we call task workers, which are separate processes. They're going to execute them for you, and they're going to give you them back. So if we were to run this, notice that we have this concurrently method being called. We're passing an array of tasks we want to execute. If we were to run a benchmark and just run the 3 of them and see how it behaves, you would notice that we have this. So this is in milliseconds. Each query is taking roughly 6 seconds, but you can see that the total operation only took also 6 seconds, and is very close to the duration of the 3rd query. And that's because since you're executing things concurrently, the entire operation time is going to be this lowest operation duration. So if you have an application that's either doing things in a way that you don't depend on previous executions on previous queries, you can leverage this. But you can also design your application if you need high performance in such a way that you can execute tasks independently. So, for example, if you have an e-commerce checkout, what you usually do is you would create an ordered record in the database, then you would create an order item record, then you would create maybe a checkout object, a bunch of things that depend on that first order object being created. You can also design your application in such a way that you can handle creating all of those in one go, maybe using an UUID. If you have a UUID that you can use for all of your database records, then you don't have to wait for the first database record to be created. You can create all of them concurrently. So although not intuitive, there are a lot of opportunities if you want to have a particular endpoint or a particular application to be high performant, where you can execute lots of operations concurrently, not limited to database calls, but also to cache calls, to HTTP calls, external services, all of that. It's not intuitive, it's not how we usually do things, but you can change the way you code to leverage those functionalities. Okay, that's all very cool. Why is this not the default? And the reason this is not the default is first, PHP wasn't intended to be like this, but why hasn't it changed? And the reason is, yes, you get more performance, but it's not as intuitive as a shared nothing architecture is. There are some gotchas. Most of them are related to global state, And there's also the problem that you have millions of PHP applications running already. So if you were to make this change, you would break pretty much all of them. Some of the gotchas. Imagine that you have a cache class, and you're just caching some stuff in memory. So you're passing a user ID, maybe you're hitting an HTTP API to get the result. So you say, OK, for the duration of a request, I want to cache that result. And you create a simple class that stores that in memory. In a typical PHP application, you would expect this to be reset between requests. So you're only caching things for the duration of the request. And obviously, if you get another request, the cache would be clean. If you run this in a long-run environment, here's what's going to happen. You're going to have your first call. Let's say that you want to check how much a person has paid for the last order, and that's in the user object. The first call is not going to hit the cache. It's the first one. The second one is going to hit the cache. And then maybe request 450. It's also going to hit the cache because the application was never reloaded. So you have lots of these gotchas, which folks in other languages are used to, so they usually code prepared for that. But in PHP applications, that's not intuitive. In this scenario, you would also hit the cache at request 450 if you're looking for the same user. And by the time that user last payment amount might have changed, you might have stale state. So that's something you have to look out for. Another example, let's say you have an API call logger and you just log in API calls. Again, you assume that that's going to get destroyed at the end of the request. So I don't have to worry about that. But if you have a long-run environment, that's going to keep running and running and running and running and running and leaking memory. And at some point, this might be a problem. Now, thankfully, Octane has also thought about that. And Octane will periodically restart your worker. So after 500 requests or so, it is going to restart it, just in case you have one of these problems. So it does a lot of things. And now you might think, OK, this is all pretty cool. When can we use this? Obviously, high-traffic applications would benefit from this. First, because you're going to improve the response time since you don't have to boot the application. You can do some operations concurrently. You're going to massively decrease that. And you can also improve the amount of requests per second, precisely because you can handle more requests in a given second at a lower duration. If you want to decrease your infrastructure costs, this would also help you because you would decrease the allocated CPU time. Since you spend less time in each request, you don't have to boot the application, you don't have to wait for all I/O operations, and you would also decrease the memory usage in that sense. And although non-intuitive, the amount of CPU time you're saving is not necessarily how fast the request is, because a lot of the time is spent putting the application. So it could be greater. It could be orders of magnitude cheaper to run this. And obviously, reduce latency. If you have an endpoint or an application that depends on being very fast, maybe you're hitting a cache. So if you have a route that only hits a cache, you spend basically the entire duration of the request putting the application, and then you just hit the cache, which is super fast. With Octane, you skip the entire boot duration. And obviously, Octane also offers, the Runtimes also offers additional capabilities that you can tackle into while using Octane. You're already using the runtime. You can look into other features. For example, Swole offers WebSockets connections, TCP connections, and more. And finally, if you want to go a bit deep dive, do a bit of a deep dive into this and look in some other subjects, you can look into file descriptors to understand how servers like Nginx work. You can look into event loops to understand how also servers like Nginx work and how Node.js works. You can look into coroutines. You can look into Go routines to understand how the Go runtime handles that sort of problem. And obviously, you can also dig into Swole and FrankenPHP. And that's pretty much all. Thank you all.
Well done. Well done. Don't worry about all these elephants. I'll explain those later. When in the application or the product lifecycle should you start thinking about Octane?
I think there are two situations where it is very interesting. First, if you already have an application that's already running and slow response times are a problem or a slow throughput is a problem, instead of migrating that into something else, looking into Swole could be very helpful. If you have applications that are costly to run, sometimes looking into Swole, into Octane could also solve many of your problems.
So before bailing out altogether because of throughput, look at Octane first.
Yes, for sure.
Okay, second question. Do you not have a favorite driver, but a driver that most people should reach for first? Maybe a general purpose driver, or is that not a good question?
Slow is battle tested.
Okay.
Lots of big companies using it.
Okay.
But FrankenPHP is very promising. One of the coolest things about FrankenPHP is that it not only replaces PHP-FPM, it also replaces Nginx. So you have less things to worry about. It's very performant. It is an excellent driver, and I would definitely look into both Franken and Swole.
Is it 1.0 now, I think? Franken?
It is.
All right.
Released, yeah.
Okay. All right, y'all give it up for Mateus. Good job, man. Crushed it.